This paper was published in Monthly Notices of the Royal Astronomical Society. It explores topics such as black hole X-ray binary, jets, cosmic water hoses, blast wave, space, splash, relativistic speed, Lorentz factor, and interstellar medium, ISM density. Let's first hear a simple explanation.
How fast and powerful are the big jets from black hole star pairs, and how do they change the space around them? A black hole X-ray binary is a system where a black hole and a normal star orbit each other. Gas from the star falls toward the black hole and can make bright X-rays. Sometimes the black hole also shoots out narrow beams of particles called jets that move almost as fast as light. Imagine a garden hose spraying water very fast. The jet is like that, but much thinner and much faster. Astronomers watch these jets with radio and X-ray telescopes as they travel far from the black hole. In this study, up to about 0.6 parsecs, which is almost 2 light-years, about twice the distance from the Sun to the nearest star. Scientists use a blast wave model, like the ripples from a rock thrown into a pond, to understand how the jet slows down when it hits thin gas in space. The researchers modeled the full motion of jets from 3 black hole X-ray binaries and found how fast they moved, the angle they flew out, and when they were launched. They measured the jets' total energy and found it to be between 10 to the power of 43 and 10 to the power of 44 ergs. That is like the Sun's total light energy for tens to hundreds of years packed into the jet. They also found that the space the jets travel through is very empty, from about 0.4 particles per cc down to 0.0001 per cc. For comparison, Earth's air has trillions and trillions of particles in the same space. The study shows that models used for gamma-ray bursts, huge cosmic explosions, work well to describe these black hole jets too. Knowing the jet's speed and energy helps us understand how black holes push energy into their surroundings, like how a strong wind can shape sand dunes. Finding that the jets travel through very low-density space explains why they can go so far before slowing down. This helps astronomers learn how black holes grow, how they affect nearby gas and stars, and how similar cosmic explosions are to each other. In short, it tells a clearer story of how black holes change the space around them and how powerful their cosmic hose can be.
Ready for the next level? Here comes the science explained with real research terms.
How powerful are the big jets from black hole star systems, and how do they change the space around them? Black hole X-ray binaries are systems where a black hole pulls gas from a companion star. As gas falls in, some of it is launched away in narrow, fast jets that can travel huge distances. Think of them like cosmic water hoses or fireworks shooting out from the black hole. These jets move so fast that Einstein's relativity matters. Scientists describe the speed with a Lorentz factor, which tells how close the jet speed is to the speed of light. When a jet hits the thin gas between stars, the interstellar medium, or ISM, it makes a blast wave, a bit like the ripples and splash when a fast boat hits calm water. By watching the jets slow down, astronomers can work backward to figure out how fast and energetic they were and how dense the surrounding space is. The researchers modeled the full motion of jets from 3 black hole X-ray binaries that were observed up to about 0.6 parsecs from their sources. Using blast wave models, similar to those used for gamma-ray bursts, they found reliable values for each jet's launch time, angle, and relativistic speed. They constrained the jet's kinetic energies to about 10 to the power of 43 minus 10 to the power of 44 ergs, and placed upper limits on the ISM density the jets moved through, ranging from less than about 0.4 particles per cc down to less than 10 to the power of -4 particles per cc. Overall, the results support the idea that these black hole systems sit in fairly low-density environments. Knowing the jets' energy and how they slow down tells us how black holes put energy into their surroundings, like measuring how strong a boat's wake is to learn how fast the boat went. This matters because jet energy can heat or push around the gas that later makes stars, so jets affect their local galactic neighborhood. Also showing that models from gamma-ray bursts work for these smaller systems hints at common physics across very different cosmic explosions. Finally, finding very low ISM densities helps explain why some jets travel far before slowing, and why we sometimes have a hard time detecting their effects.
That's it for today's paper. Thanks for tuning in. See you next time.